Hey, this is Tony from Adafruit, and in this video I'm going to look at a fun project to build a tachometer, or a device that can measure how fast something spins with a circuit playground board. And the idea is, if you have a fidget spinner like this, you can see how quickly it's spinning around by just holding it next to a circuit playground, and it can actually detect the speed of the movement of the spinner. And so we'll look at how to create this with the Arduino IDE. And then maybe in a future video we'll see if we can do this with CircuitPython, but this video will be focused just on Arduino. So let's dive in. I'll do a quick little demo of how this works. It works with both the Circuit Playground Classic and the Circuit Playground Express boards. I'll mention a little bit more about those when we look at the demo here in a second. But I'll show you a quick version of the demo. I'll show you how you can load this example sketch, and if you just want to play with it and see how to use it, but you don't really care how it works, I'll point you towards the code that you can use to load it up. And then I'll just go into how I created this, and we'll look at a little bit of some of the basic signal processing that I'm doing to detect how quickly that this spinner spins around. So without further ado, let's dive in and look at a demo. We'll go to the workbench shot real quick. So on my workbench over here to the left, you're basically seeing a shot of, this is a Circuit Playground Express board, but like I mentioned, this works with both the Classic and the Express. And by the way, I'll put a link in the description down below when this goes up on YouTube, so you can find the products and things that I mention, any of the web pages I mention, and the code that I have will be down there. But the Express board, this is the newest version of Circuit Playground. It uses the Atmel SAMD21 microprocessor, really nice, fast microprocessor with a lot of memory. But there's also the Circuit Playground Classic board, which looks a lot like Express, but look on the back, you can see the Circuit Playground board just says Circuit Playground, or it might say Classic on the new ones. The Express boards say Express. This works with both versions though, so it doesn't matter. Whatever version of the board you have, this is going to work great. And I have it hooked up to, this is a 7-segment, a 4-digit 7-segment LED backpack display. And again, I'll put a link in the description when this goes up on YouTube so you can see this display. And there's a guide that I'll publish also next week that will explain how to wire this up. You don't have to use this display. I'll show that this can just output data on the serial monitor that you can read from your computer. But this makes a nice little visual display. So if I spin my spinner, and if I hold it next to, like, you might notice there are 3 LEDs. Oh, that's kind of funny. When I was holding my finger near those LEDs, it's kind of picking up some of the frequencies. But those 3 LEDs are lit because they're shining light up. And then really, you can barely see in front of my finger right there, there's a little graphic that's an eye, like someone's eye like this. That's the light sensor that's on Circuit Playground. And so both the Express and the Classic Circuit Playgrounds have a light sensor, and it's just a simple little photocell. But using that, I can actually detect when light bounces off of the spinner, and when it's moving around all these different arms on the spinner, as it gets closer to the sensor and then it gets further away from the sensor, that changes how much light that the sensor will see, and I can actually detect that and turn that into like a revolutions per second value. So this display is going to display how many revolutions per second the spinner is making. It's not revolutions per minute if you've actually used a real tachometer, like something like this, and we'll look at this in a second. This is actually a little handheld tachometer that works on the same principle, but it will output your revolutions per minute. I'm going to output the revolutions per second just because it makes a little more sense to me. So this is going to tell me how many times per second is this spinner making a full revolution. So let's spin it around, and I'm just holding it directly above the light sensor. And notice you can see it's showing like 17, 16, 15.21, 14.2, and so it's slowing down, which makes sense. I expect this spinner, like the inertia and the friction is going to slow it down over time. But it's spinning, a little bit more than 10 times a second. So that's pretty cool. And like I mentioned, I'm just holding it above that light sensor, and it's able to pick up that speed. So let's see if I can get it even faster. I think the fastest I've ever gotten this is like 19 times per second. So let's see, I'll really crank this and see. Oh, that didn't feel like a very fast one. I wonder if there's a trick to like very fast spinning. So let's see, we'll hold this above it. Ooh, look at that, 22.3. That's a new record for me. I've never done 22 times per second. So that's pretty cool. And this, it's a neat demo of what you can do with just a little light sensor. So I'll show you, like I mentioned, I'll show you how to load this sketch And if you just want to do a basic little tachometer with only this circuit playground board, that's all you need. This display is optional. Then you can just follow along with that. And then after I show you how to load this, I'll walk through how I created this sketch and how it works. We'll look at kind of the data, the sensor readings that we're getting, and kind of how I process that data to figure out the revolutions per second value from this. So let's start with the desktop view. Let's go back to that. Let's see. Okay, there we go. So yeah, we'll see everything here. Okay, so like I mentioned, this is actually a sketch that I added to the Adafruit Circuit Playground library. So like I mentioned, you need just a Circuit Playground board, either the Classic or the Express, and that's it for the bare minimum. If you want to add the display, I have two versions of this example. There's one example that uses the display, and there's one example that does not use the display, so just pick whichever one you want. But if you want to use the display, like I mentioned, you need this little 4-segment or 4-digit 7-segment LED backpack display. You can find this in Adafruit shop. I'll put a link in the description when this goes up on YouTube, and there'll be a guide that you can follow that will point you exactly to the products that I'm using here. But anyways, you want to grab the latest version of the Adafruit Circuit Playground library. A link will be in the description below. Basically, grab this code. You can probably go into the Arduino IDE and do the, let's see, the library manager, and then update your library through the library manager interface here. That should get the latest version of it, although just be aware if you're viewing this video as of like a day or two after being published, this hasn't been updated in Arduino's library manager, so you're going to have to pull this library down manually. And also one other little caveat, there's a bug in the library right now where it's broken for Circuit Playground Classic, unfortunately, so that'll be fixed really soon. But just FYI, use the current version of this library on the library manager in Arduino's system, and you'll be okay. And then just manually download this example right now if you don't see this example. So you can go to this GitHub repository, and inside the examples folder here are where all of the example files live. And the two examples I added are the tachometer example. This is the basic one that you don't need anything else other than a Circuit Playground Classic or Express board. And then the tachometer LED display version, which works with a little LED display like I'm showing right here. So let's just start with the tachometer example. And so I've actually got it loaded up in Arduino. And like I mentioned, like once the library is updated, you can just open up the example and grab the tachometer example either with or without the LED display right here. So this is the version without the LED display. And there's really nothing that you need to do by default. The only thing that you might want to change at the very top, there's a define that I have right here, this spinner arms define. And so this is how many arms does your spinner have? So you can see this spinner has 3 arms. That's basically like 3 protrusions that stick out. I've seen a bunch of different spinners these days. Like there's some real fancy ones that have all these little like brass weights on the side now that have multiple arms. So you want to adjust this value to the number of arms or protrusions that your spinner has. I've seen some spinners that just have like 2 arms. Maybe there's a no arm spinner, in which case you might not be able to use this example with it. Because what this is doing is it's looking at when the spinner spins, we'll see this signal. I'm going to dive more deeply into this when I explain how it works, but you'll see a pulse in this signal. And that pulse is correlated to every time one of the arms of the spinner moves in front of the light sensor. So it moves in front of it and you get a nice increase in the signal, and then it moves away and you get a decrease in the signal. Now that's going to happen every time an arm of the spinner moves in front of the sensor. And so one full revolution of this spinner has 3 arms. So to compute the actual revolutions per second of the entire spinner, I need to know how many arms are on the spinner, and so how many of those pulses I expect to see. And so this is like a scaling value that I use for this. If I didn't really care, I could actually set this to a value of 1, which just means that don't do any of this arm scaling logic and just give me the raw revolutions per second value that it's reading. So every time an arm passes by the light sensor, it's going to count that as a revolution of the spinner. So your RPM or your revolutions per second value might not match the reality of your spinner, but it's kind of interesting if like you're measuring something maybe that doesn't have multiple arms potentially, if you're looking at the speed of something else, because you could in theory measure the speed of another object, any kind of spinning object. The only caveat is that we'll see more when I look at how this works. You have to hold the thing really close to the light sensor, like right above it, but not touching it. So this is not good, for example, if you had like a car engine or something, you're not going to want to put a circuit playground right next to the drive shaft of your car, for example. So not a good way to use this project with something like that. But for a little fidget spinner, it's fine. Anyways, though, so make sure to set this spinner arms value to the number of arms on your spinner. And then the other values you don't have to change. We'll look more at what these values mean when I dive into how this works. But there's basically a sample depth which controls how many samples it will take when it's trying to figure out how fast the spinner is spinning. There's a sample period in microseconds. This is how long it waits in between each sample. So both the sample depth and the sample period kind of control the range of RPM values that this thing can detect. Because it all comes back to signal processing and sampling kind of laws and frequencies. It's all Nyquist's law, where basically you can only measure a signal that's as fast as half of your sampling rate. But there's also maybe a converse to that too, in that if you're trying to detect how often a signal occurs, if it's a very slow signal, like one that only happens maybe once a second, then I actually have to have more than a second of data to be able to see that complete change in the signal. So there's kind of a trade-off here because, in a perfect world, I would just measure everything and at a very, very fast granularity, as fast as I can measure it, so that I can see both a very fast signal where I need a fast sample rate to see that signal. It might just be a few microseconds in between each cycle of the spinner if you really crank it up fast. But the trade-off is, since I have to store all these samples, I don't have enough memory to store like millions of samples. The Circuit Playground Classic board only has 2 kilobytes of memory. The Express board has 32 kilobytes, but even that's not a ton of memory. So there's a trade-off here in that how frequently you sample and how many samples you take kind of controls the range of values that your spinner can detect. And so the default values that I put in here of 512 samples with a delay of 1.5 milliseconds in between them. This value is in microseconds, so there are 1,000 microseconds in a millisecond, and then there are 1,000 milliseconds in a second, so it's actually 1,000,000 microseconds in a second. But anyways, with these two default values, you can detect a value that's anywhere from like well above 20 times a second to like once a second is kind of the lowest value. So once this thing gets spinning slow enough that it's only going once a second, you won't get accurate readings anymore from this. And we'll see more about this when I dive into some of the signals and we look at this. The threshold value, this is basically how this how this thing can detect what the steady state is that it sees right now with nothing spinning in front of it versus when something is actually spinning in front of it. Because you can see once something is spinning, then the display actually updates and it starts showing the values here. And so there's a certain threshold, and we'll see what this means when I look at the signals and how this thing works. But basically, this is the amplitude, the minimum amplitude of your signal that it needs to see before it actually starts trying to count the frequency of it or detect how fast that signal is occurring. And so this just filters out the noise. It's a value that goes from 0 to 1023. That's the range of the analog to digital converter on the boards. And basically, the higher this value, the stronger your signal has to be. And so that maybe means the less sensitive that this device gets. And maybe the lower the threshold, then the less strong your signal has to be. But that means you might get more noise because, for example, the lights in my room are LED lights. Those flicker at a certain rate, and this sensor can actually pick up that rate of flickering. Even normal incandescent light bulbs flicker at a rate of like 60 times a second just based on the 120 volts alternating current in your house. So, you'll get this cyclical noise, and it's this threshold value is a way to kind of filter out the high frequency noise that you don't care about. Not necessarily high frequency, but the noise that's not strong enough, that's not like a spinner right in front of the sensor with a very strong signal. You want to filter out anything that's not that kind of a strong signal. And so this threshold helps control it. This 400 value seems like a good value that, at least in my testing, works pretty well. Although I have my spinner is white, which means it reflects light a little more easily than if you had like a black spinner. So if you have a dark colored spinner, you might need to adjust this threshold value potentially. If you see a lot of weird noise, like it's just showing values and there's nothing spinning in front of it, you might want to increase the threshold value. And likewise, if you put a spinner in front of it and there's absolutely nothing happening, it's not updating things, you might want to drop the threshold value potentially to see if that helps with it. And then this measurement period in milliseconds, this is just the spinner will take a measurement every number of milliseconds specified here. So every second, 1,000 milliseconds in a second. Basically every second it's going to update the display and it'll print out the measurements of this. And now, okay, so like I mentioned, this tachometer example is what I need. You just modify this to have the number of spinner arms. I'm going to actually show this. Here's a Circuit Playground Classic board. So I'm going to connect my Classic board, and I will load this sketch onto it. Let's see if we can maybe see this. I'll keep this set up here. I'll put this Classic board kind of down in the corner here so you can kind of see it. Okay, so now let's just say, let's just make sure I have my board selected. So I have the Adafruit Circuit Playground. This is the Classic board. If you're using Express, make sure to select the Express board from the Adafruit SAMD package, because there's you might see in the Arduino SAMD package, there's also a Circuit Playground Express. This is an old version. You don't want to use this one right now. It'll be updated eventually. But anyway, stick with the Adafruit packages, the Adafruit SAMD package if you're using the Express board, or for the Classic, stick with this one. Select the board, and then here's the serial port for the board, and let's upload this sketch to my board. And so this is uploading to the board right here, and this is going to put this little tachometer sketch onto the board, and then in a moment it's going to finish. So it just uploaded, and once it's uploaded, then open up the serial monitor in Arduino, and you want to open this and change it to 115200 baud. It might be at like 9600 baud sometimes. And this is just going to show every time it detects the spinner with a high enough threshold, and you see some noise sometimes at the start here. But when it detects that threshold, when the signal is past that threshold that I mentioned, it's going to start printing out the revolutions per minute, the frequency, which is kind of the revolutions per second, and also this period value. And we'll see more about what those mean, but let's just try it. Let's see what happens. So again, I'm going to hold this above the light sensor. Oops, I just touched the board like that. So, and you can see it's showing the same values that I was printing out. At least the frequency value is what you saw printed out with on the display over here. So that, like that 7 and that 11 value and stuff like that you're seeing, that's what the display was printing out, is this frequency value here. So that's how many times per second is this spinner doing a complete revolution. And then the RPM value is basically just converting that revolutions per second into revolutions per minute. You just multiply by 60 because there's 60 seconds in a minute. And so you get that value. This period is the amount of time in seconds in between a complete revolution of the spinner. So it just kind of tells you like how fast that thing is moving. And all these values are related. Like if you know frequency, you can calculate the period. You just take the inverse of the value. So they're all kind of the same value, but this is just different ways to look at it. So again, I'll just hold this above the light sensor like this, and we'll see, oops, as I hit the sensor. So you can see it kind of falls down to slower values as it goes. But it's reading a value of around, maybe 700, 800, 900 revolutions per minute. So we can actually double check that though. So like I mentioned, I have this thing. This is a little digital tachometer that I got on Amazon. I'll put a link to this. It's like $12. And this works off of the same concept. So, you notice I'm holding the light sensor, or I'm holding the fidget spinner right in front of this light sensor on the Circuit Playground board. Well, this tachometer, so it has this test button, and you might see if I press test, it's actually flashing a light out the front. And it's, as far as I understand, using the same logic. It flashes, it sends a light out. I think it's just an LED. I think they're fancier ones that use lasers. A $12 one, I'm probably not getting a laser tachometer for $12. But it shines a light out, and then it measures how long it takes for that light to come back so that it knows, how far something is from it. And then it's looking for a cyclical signal. So when something's rotating, it's assuming that there's maybe something that's sticking out further or something that's maybe more reflective, so that every time that reflective thing spins in front of this light sensor, it'll pick that up as a stronger flash, and then it's figuring out how often that happens, and then it can calculate the RPM. And the way these things work, it's kind of interesting. They come with these little strips of this retroreflective tape. So this is just tape, but it's reflective so that when the light shines on it, it reflects a lot of the light back, so it makes it brighter. And what you're supposed to do is cut off a little piece of the tape, and you put this reflective tape onto the spinning thing that you want to measure, and then you can use this little tachometer to measure it. So let's just try it. I cut off a little part of that reflective tape, and I'm going to put it on the edge of my spinner, and we'll see if I can read the values, or at least we'll see what this proper digital tachometer thinks. Although remember, it's only a $12 one. But we'll see if we get values that are around, 800, 900 revolutions per minute, because this thing measures in revolutions per minute. It doesn't happen to show in revolutions per second. Okay, so my fingernails are not very long, and so this could be a 20-minute stream of me trying to take tape off of the backing material. There we go. I think I got it. Okay, so I'm just gonna stick this on the edge of the spinner so that when it spins around, it'll have like one reflective part that shines more brightly, and this tachometer can pick it up. So I'm gonna put this on the edge of the spinner like that. So you can see I just put that little strip on there so that it's gonna spin around, and every time that strip comes in front of the sensor, it should reflect back the light and hopefully give us a good reading from this. So okay, so I'm going to spin this guy really fast, and let's see if I can show the output of this thing. I have to kind of shine the light in front of it, so it's hard for me to do this all at once, and you have to kind of get it right in front of it, a little bit far away. Okay, let's see this thing. There we go. Let's see, it's showing. If I hold it like this, let's see if I can hold it like that. And we're seeing about 600, 700 revolutions per minute or so it's measuring. I don't know if you saw that very well, but 700 RPM or so as it slowed down, which that's pretty close to the values I was measuring right here. So for example, if I let this spin and then if I let it slow down a little bit again, or actually here, maybe I'll hold it in front of the sensor like that. So you can see I'm measuring, let's see, a value of like 500 RPM. And then if I put this in front of it, you probably can't see it yet, but I'll tell you what value it's measuring. Yeah, it's about 400 or so RPMs a second ago there. So it's pretty close, I think. At least I'm willing to say that this is close enough. This Circuit Playground was measuring about 600 RPM, and this $12 tachometer was also measuring about 600 RPM. So that seems correct to me. I don't know how accurate this Circuit Playground thing is. I wouldn't if you have high-speed machinery, for example, that someone's life depends on, do not use this for that measurement. But for a fidget spinner, hopefully no one's life depends on a fidget spinner, so it's probably good enough to measure this value. Okay, so that's all you need if you just want to run this sketch and just look at the measure a fidget spinner, which I guess, is that a contest nowadays that the kids are doing, where you're trying to see who's got the best fidget spinner. Back in my day, the fad that I remember when I was young was something called Pogs, which were like these. It was like this Hawaiian bottle caps or something, I want to say, where like you would stack up all these little things called Pogs, and then you'd have a slammer, which was like a really heavy one, and you have to throw it down. It was kind of like marbles, but like also, I don't know how, I never really played it, but I just remember everyone had these little Pog things, and everyone had these slammers, and the fidget spinners remind me of that kind of trend, although the fidget spinners are still just genuinely kind of neat. But anyways, if you just want to measure your fidget spinner speed, load up the tachometer example, open up the serial monitor, and that's all you need to get the speed like this. And then, like I mentioned, there's also an example that has with the LED display, like I was showing over here on the workbench. And so that's if you wire up to your Circuit Playground, let's see, so if I load up this example, you need, like I mentioned, a 4-digit 7-segment LED backpack display, and you connect that to, so that's an I2C device, which means it has a clock and a data line. And so you connect the SCL line to the clock line on Circuit Playground, and the SDA, or the data line on Circuit Playground, goes to the data line on the device. And then 3.3 volt power to the display, and ground also goes to the display. And then on this one, there's one extra configuration value, your display address. This is the I2C address of your display. The default value is actually 0x70, which is probably what you want. My display, I happen to change that address to 0x72, so that's why I modified it. But then load up the sketch, and what it will do is it will behave exactly the same. It will also print out on the serial monitor, so you can open the serial monitor and see the output, but it will print that frequency value, or the revolutions per second, on the display like this. So I just kind of breeze through this because there'll be a guide that I'll publish maybe next week, where I'll actually show the wiring for this so you can see how to hook this up to the board. But again, like you don't necessarily have to have this display. You can use the serial monitor to see how this works. Okay, so let's look at how does this thing work? Like, what is this magic where, I'm holding this thing in front of a light sensor. It's not touching it, but it's still able to detect how fast it's moving, just based on the light that's bouncing back. So how do you do that? And let's go through kind of what this signal processing looks like, because it's kind of fascinating, and it applies to a lot of other things that you might do with signal processing. That's the basic thing that's happening here is I need to detect the frequency of a signal, like how often a signal changes, because once I know that, then I know how fast this thing is moving. So we'll see an example of how to do that, and you can apply this to a lot of different things. Like audio, for example. If you're detecting the frequency of audio, that could tell you if there's a tone being played, for example. So very, very useful kind of concept to look at here. So okay, we'll start with looking at an example from the Circuit Playground library. I guess I'll use the classic board again down here, and we'll kind of build up from scratch what I did. So open up under Hello Circuit Playground examples. These are like the most basic Circuit Playground examples. Grab the Hello Light Sensor example, because this is like the most simple light sensor example. I'm just going to close my tachometer sketch example here. So what this sketch does is just every second it will print out the light sensor value. So we'll just save this and we'll load it up on my Circuit Playground right here, and we'll just see what this thing looks like. And so it's going to print out the values, and you'll just see the raw light sensor value. Okay, so if I open up the serial monitor, and for this serial monitor, I need to open it up at 9600 baud. So, oops, let's see, it's still uploading to the board. Oh, I opened the serial monitor as it was uploading, which is a big no-no, because now it's gonna crash Arduino, or might not crash it, but it's gonna fail the upload. So let's just cancel this. Let's upload it again and wait for it to finish, and then we'll open up the monitor. Okay, here we go. So it's gonna do its upload in a second. So it's uploading. There we go, now we're done. Okay, so now let's open the serial monitor. And if I open it at, I'm going to change it back to 9600 baud just because that's what the sketch has, and sometimes you won't see the output if you don't get it right. But this is showing the raw output of that light sensor. And so the way this thing works, if I cover up the light sensor, you get a lower value, whereas if I take my hand away and more light is hitting it, you get a higher value. And so you can imagine, like my hand covers it up, like it's shadowed, you get nothing. My hand moves away and you get a high value. So imagine my hand is kind of that spinner, moving in front of this thing. So you can see I get high values, and then my hand moves in front of it, and I get low values, and then my hand moves away from it, and then I get high values again, and then maybe my hand moves back in front of it and I get low values, and then it moves away and I get high values. So that's really what I want to detect, is how often that happens. But obviously the spinner spins so fast that, if I'm taking a measurement every second here, it's never really going to know. This thing's moving 20 times a second. So if I'm only measuring once a second, I cannot detect 20 times a second. You have to measure actually twice as fast as your minimum frequency that you want to detect. So if I want to detect 20 times a second, I have to measure at least 40 times a second to be able to detect that. Okay, so let's change the sketch then. So let's tweak this a little bit. I'm going to remove this light sensor value printout, because what I'll show you is we can use the serial plotter in Arduino to give us a graph of this output, which is a little more interesting because we can see these changes kind of visually. And then let's just get rid of this delay. Let's have it run as fast as possible. And in fact, let's increase the baud rate of the serial output, because 9600 kilobaud is pretty slow. We can go faster, and the faster we can go, that's just the faster I can get this data output and put into the serial plotter. So let's run this, and we'll load this onto our board. And we'll wait for this to upload. So there we go. Okay, now I'll open the serial monitor again, and I'll switch it to 11.5200 baud. And you can see this thing's moving pretty fast now, so I'm not going to be able to really notice. I put my hand in front of it and it goes down. I put my hand away and it goes back. I can spin the spinner, and we'll see, like, the values are maybe changing. It's a little hard to tell, but it's, there's something happening there. But here's what you want to do. Since I'm only outputting a single number, you can open up the serial plotter instead of the serial monitor, And this is actually just going to give you a graph of all the values. So it's just showing like the last few thousand values inside of here. And you can see there's this up and down signal, which is kind of cool because this is actually showing the light level in my room. And there's some high frequency noise to this light. It's basically like I mentioned, the light itself, the LED lights sometimes have a flicker that's inherent to the way they work. If it's an incandescent light, you might have some flicker. Same thing with your fluorescent lights. But if I move my hand in front of this, the values change. You can see the values get really low. The serial plotter on the left here, this is the scale of output values. And so these values go from 0 to 1023. That's the maximum value of the light sensor output. And this thing will auto scale. So, it's down on these really low values. And so you see that, it's getting values that are from like 0, like 1 to 2 or so. But I take my hand away and you can see it shoots back up real quick and then it auto scales. And so it, looks like it's filling, it looks like the signal's the same, but notice these values are much different. So, I'm up in like the 450 kind of range of values here. Whereas when I cover it up, I'm down in like, the 2, 1 kind of range for it. So that changes a little bit. But let's just see. So this is the steady state. What happens when I put the spinner in front of it? So now I've got the spinner in front of it and things are different. This signal is obviously changing. There's still a lot of noise in this signal, but it's interesting that as this spinner kind of slows down, I'm noticing the signal is kind of slowing down a little bit, or at least how often the peaks in that signal occur slow down, which is just kind of showing, my assumption that I mentioned before, that as the arms of the spinner move in front of the light sensor, that's changing how much light is reflected back onto the sensor. And so it gets a stronger or a less strong signal. And that just appears as, your peaks occurring faster or slower. We can make that a little more apparent though if we turn on the lights, because notice I don't have the lights turned on this board, but if I turn the lights on, then that's going to reflect a bunch of light up, so I'll get more light, and so I can hopefully see that signal a little more clearly. So let's do that. Let's change our code a little bit, and let's just add in circuitplayground.clear pixels. This is going to turn off all the pixels, and then let's call circuitplayground.setPixelColor. And let's set pixel 0 to the color 255, 255, 255. This is basically your red, green, and blue color. If they're all set to 255, that means white. Like you want full white brightness. But there's one little thing. By default, the Circuit Playground library dims down the brightness of all the LEDs, but I don't want them to be dim. I want them to be full bright. I want as much light as I can output on this so that I get a better reflection back. So in the begin function, if you pass a value, of 255 to this is the brightness of the LEDs. So by default, it cuts the brightness down in half or so, which makes sense because if you're building like an animation, you don't want to blind yourself with it. But in this case, I really do want blinding light. So I'm telling the library, use full brightness for my pixels with this 255 value. Then I clear them, and we'll turn on the first pixel, and then let's turn on the other pixels that are next to it. So we'll turn on the first 3 pixels. So pixel 0, 1, and 2. So these will be the first 3 pixels that are right next to that light sensor on the board. So we'll do that. And I'm not changing any of my loop logic, so it's just going to output, it's going to read the light sensor as fast as it can and output the values. So notice I just loaded it and the lights turned on. So let's open up the serial plotter and see what we get. And let's see, I'll hold this in front. And so now this looks a little bit different. Like, notice, remember before with the lights turned off, it was really jaggy and it's kind of hard to tell what was happening. It's hard to tell like where there was a peak in the signal and where there wasn't. There was just a lot of jagginess to it. And then, when I take this away, I get kind of that same steady state. But when I turn the lights on, it's nice in that I don't see that jagginess. I get a really distinct signal so that when I'm holding this in front of there, I see these really nice peaks in the signal. And then as it slows down, the time between those peaks is increasing, so that the frequency of those peaks occurring is kind of related to the frequency of the speed of this spinner. And to make this a little more apparent, let's actually change this code so that what I'll do is I'll take a window of samples. I'll take like 1,000 samples or 500 samples, and I'll just save them. And then if I'm holding the button down, I'll print them out so that the serial monitor will show them. But if I'm not holding the button, I won't print them out. So that way it'll just let me take a quick snapshot of, just get like 1,000 or 500 samples, and let's just see like a snapshot of that signal so that we can start to look at what's the difference between this steady state signal, like right now when, there's no spinner in front of it, versus how does that compare to when the spinner's in front of it, so that we can see what the difference is. And then once I know the difference, we'll see how can I write some code to actually detect that difference. Okay, so let's change this code then. Instead of just printing out the light sensor as fast as it can, what I want it to do is if I press either the left or the right button, I want it to print out like the last 500 sensor readings that it saw, so that I can just take a quick snapshot of things. So what I'm going to do is I'm going to change this main loop. I'm going to have it run just once a second. I'm going to have it delay for 1,000 milliseconds. So that just means that, it's only every second it's going to check to see if the button is being pressed and then grab a bunch of measurements for this. Okay, so instead of grabbing one measurement, what I'm going to do here is let's take an array of measurements. So let's say samples, and let's actually set a define. I'm not going to use this int value up here. So we'll say define sample depth, and let's say 512 samples to start with. And so we'll say sample depth. This is just how you make an array in C, C++. And I'm going to use this syntax, which might be new to you if you haven't used C and C++ in a while. This is the Initializer Syntax in C++ 11. This basically just means that it guarantees that all of the values in my sample array will be set to the value 0 when you start with. Because technically, I think in older versions of C, if you define an array like this, the value of memory for these values could be random. It might be it might be set to 0 if you're lucky. It might be some array that was just previously used and you're getting all these random values in there, and that's a source of a lot of bugs. A lot of native code has problems where you forget that uninitialized memory is set to random values, and maybe in your testing you never hit those random values. You always just happen to see 0 values and everything works, and then you put it in production and everything breaks. So be careful and be aware of what your memory is set to. Anyways, so I'm going to make an array that has 512 values inside of it. Each value is an unsigned 16-bit integer. That's just a large enough value that can hold that 0 to 1023 value that the light sensor function gives me. And then let's just grab that number of samples. So a quick little for loop. We'll say, well, I is less than my sample depth. And then we'll increment I. And let's just say samples I equals circuit playground dot light sensor. So this is just going to save in that array of 512 samples that's defined by the sample depth. So it's going to save in this array a light sensor reading as fast as it can. So it's just going to grab 512 readings. And then let's check and see. So instead of trying to print out a single value like I was before, let's look and see if my circuit playground dot left button or circuit playground dot right button. So this is how you check if one of the buttons is pressed in Circuit Playground. So the Circuit Playground library, these will return true if one of those buttons is being pressed. So if one of those is pressed, then let's just print out all the samples. So we're just going to do the exact same for loop syntax here. So we'll say we'll loop through all of our samples again. And then now let's just do a serial dot print line of the samples. Oops. So we'll say samples I. Okay, so that should be good enough. So again, what's going to happen here is this loop's only going to run once a second. And then it's going to just grab 512 samples from the light sensor as fast as it can. And if the button is pressed down, then it's just going to print out all 512 of those samples. And then it's going to go back and it's going to wait a second and do that logic again. And I'm putting that second delay in there just so that when I hold down the button, it gives me enough time to press it and take my finger away so that I don't get bombarded with, just a huge bunch of samples. There's some time here that it's not going to constantly run. Because I just want to see like one snapshot. Here are the last 512 samples of this. Okay, so let's save this and let's upload it to our device, our Circuit Playground Classic board. Okay, so it's uploaded. And okay, so now I open up the serial plotter and nothing's happening, which is good because nothing should happen until I press a button. So I'm going to press the button and I released it. So I saw it printed out some things, and I released it. And so this is cool. This is actually showing me what is the output of my light sensor. So, you know, when I hold down this, my finger here, every second it's grabbing a new measurement from, or a new set of 512 measurements. And so this is just a good way to get a quick little snapshot of what does this signal look like. You know, almost imagine like if I'm looking at an oscilloscope, but I had like a trigger function set up where I'm able to say, okay, take, you know, some number of samples and stop. My trigger in this case is my finger holding this button. So, you know, when I release my finger, it stops and I can look at this signal. So this is my steady state signal where, you know, there's nothing in front of the spinner. Let's see how this compares to with the spinner spinning in front of it. So, you know, I'm going to spin my spinner, I'll hold it in front of there, and then I'll hold down the button. Oops. And so let's see how this changes. So you can see it's definitely a different signal. So I just let go of the button. So let's look at this signal a little bit. So this is kind of interesting. You know, like I mentioned, my assumption is that each time the arms of the spinner moves in front of the light sensor, I'm going to see a peak or, you know, something like this, because, you know, imagine that hump is kind of like the distance from an arm to the light sensor. And so, you know, maybe when it's like this, the distance is really far away. You know, there's no arm. You know, imagine my sensor is like right here where my finger is. There's a high distance here. And so, you know, think of this, the value right here as the distance from your light sensor. And so this might be one of these little kind of troughs of the signal. And then, or I guess it's actually a peak of the signal, but it's a trough of the spinner in the sense that, you know, there's no arm. But then as the arm moves in front of the light sensor, that distance to the sensor, you know, imagine my sensor is still right here where my fingertip is. Now that distance is much smaller. And so that might be one of these troughs of the signal right here. So, you know, it's a little bit further in time, but now, you know, the spinner has moved. So it's reading less light or more light in some cases. I guess I had the explanation kind of reversed here, where, you know, the closer it gets to the signal, the higher the intensity of the light. So, you know, if the spinner's right in front of it, we'll see a peak right here. And then as the spinner moves away, so my sensor is still here, it's going to see less light, or at least less intense light reflected on it. So you get a drop in the signal here. So that's kind of cool, because it kind of tells me, okay, you know, in this little snapshot, I saw, you know, effectively all three arms of this spinner move around. You know, here's one arm, here's the second arm, here's the other arm. So that's, in that 512 samples, that was like one revolution of the spinner that it was able to capture and see right here. So that's pretty cool. But let's look at the steady state again. So I don't have the spinner spinning. I'm going to press the button and we'll get a measurement. So, you know, here's this signal with nothing spinning in front of it. And I mean, notice though how this signal, it kind of looks the same, right? They're all sine waves. This is a signal that goes up and down, and sine waves have some properties, like there's a frequency, which is how many times it changes per second. And then there's an amplitude, which is what is the height of this sine wave. So this is, you know, the amplitude is basically from the middle point here up to the top and the bottom. That would be your amplitude value. And that is actually the key, because the big problem is, how do I tell the difference between this signal that's going up and down and, you know, this signal with the spinner spinning that's also going up and down, but just at a different rate, or, you know, in a different way? You know, how do I detect the difference between those? And if you notice the values that I'm getting for this sine wave, so this was with the spinner spinning in front of it, you know, it's going from a low value down here of like 350 or so, all the way up to a high value of like 850. So that's a big range. That's like 500 units, and there's no unit of measurement. This is from your analog to digital converter, so it's, you know, just think of it as the like light intensity. But that's a big range, you know, 500 or so units. That's half of the resolution, or half of the total values in the analog to digital converter. Let's see how that range compares to the steady state right here. So I'm going to press the button, and so in the steady state, notice our values only go from like 400 up to like 540. So that's like 140. So that's kind of a key difference here. You know, in this steady state, the amplitude of my signal is much smaller, and it's hard to see in this serial monitor because the serial plotter is rescaling itself. But if I could tell this thing not to scale itself, you know, you'd see the steady state is a real small signal, And then when I spin the spinner and we get one of the good spinning signals, you see that the values have a much wider range. So that amplitude goes from like, 300 to 900, something like that. There's 500 or more values in between there. So that's kind of my key and the trick to how this works. I want to read a number of samples from my light sensor and look for what is the amplitude of that signal. And once it crosses a certain threshold, which was the threshold value I was talking about in the configuration of the tachometer sketch, then I know something must be spinning in front of that light sensor, and let's start detecting how often or how quickly it's spinning for this device. So that's how I know the difference between the steady state versus the spinner or something moving in front of it state. So then the next question is, okay, once I have a good signal, like we'll look at a quick little snapshot here. Let's say I have that signal. How do I detect the frequency of it? How fast is it changing? And so that's the real magic of the fidget spinner tachometer here, is that I need to go from this sine wave-ish signal, or it's not a proper sine wave, but it's alternating. I mean, this actually kind of looks more like a square wave. And it would be interesting in that notice how like this fidget spinner has nice rounded edges, so that as it spins around, you'll get a nice rounded fall off of the light. As it gets closer and further away to the light sensor, you're going to get a nice smooth transition. And that's kind of the value you see up here. If you had a different spinner that had like more of a hard surface, I bet you would see a different, like a sharper value up here, which is kind of interesting. But the important thing is that I know for sure though, as the arms spin towards and away from the light sensor, I'm going to get a jump, a peak like this, and then a drop back down. So then the question is, how do I measure how often that thing occurs? And there's actually a lot of different ways to do this. So you can get really deep into signal processing and actually do some really advanced analysis. You can use something called like the Fourier Transform, where you can convert a signal that you have a bunch of time series data. You can convert that into frequency data, where this Fourier Transform can actually, given a signal, tell you what are the frequencies that it sees inside of that signal. Are there frequencies at like 2 hertz versus 20 hertz, 20 times a second. And so I could potentially say, like, let's run a Fourier transform on this signal, look at the outputs, the intensities of each of the frequency buckets, and then just see what bucket has the highest intensity of frequencies, and that must be the speed that my spinner is spinning at. That's kind of one way to do it. The thing is, though, the Fourier transform, there's a lot of math involved with it, and it's not very easy to do on these tiny little boards like the Circuit Playground Classic board. So it's maybe not a good option. Another option, though, is that if I know that this is a sine wave signal and that it's always going to go up and down, it's it's going at that rate, and there's a certain frequency that occurs at, I can just count how often does it go up and down, and then I can actually see, like, given a period of time like this 512 windows of samples here. So I know, I took 512 samples, and I know the period of time that it took for those samples to occur. I can actually measure that in Arduino. It has the micros and the millisecond function. So, given this number of samples and the amount of time that occurred, if I just count how many of these peaks that I saw in that window of time, that tells me how much time it took, or, given the window of time and the number of peaks, if I divide that window of time by the number of peaks, that's how much time it took in between each of those peaks, because I'm making an assumption that this is just a very regular signal that's just always happening at the same kind of shape, effectively, and just the frequency is changing. So that greatly simplifies my logic here, and that really I just want to count how many times these peaks occur. Now the trickiness comes in the sense that these peaks, I don't really know, like, what's the max value of this peak. In this little measurement that I took right here, this peak happened to be around like a 900 or so value. But let's see, if I get another set of samples here, then I might get a completely different set of peaks. So, this one happened to be up around 900 again, but maybe I hold this thing further away from the sensor. Maybe I get a smaller peak. So it's, I could hard code in and just say, count how many times do I see the measurements above, like I just draw a line, let's say this line at 800, just count how many times is it above 800. That could work, but it wouldn't be resilient to, if this moves further away, and if this peak value falls down a little bit further, and maybe it suddenly goes below that 800 threshold, then everything just stops working. The other trickiness too is that, this signal is above this 800 value for quite a number of samples. I mean, so you can see down here, this is just like the sample number. So, there's maybe like 50 samples or so right here where it's above that 800 value. So I don't want to count all 50 of those times that it's above 800 as 50 different, crossings or 50 different cycles that it saw. This is all just part of one cycle, like one continuous cycle. I really want to tell how many times does it cross this 800 threshold and then going up, and then how many times does it cross the threshold going back down again. So I want to see that change in the threshold. I don't want to see how many times is it above the threshold, like, this number of samples up here. I want to see just exactly what point, or, how often does it go above the threshold? Because imagine the signal, the mouse is kind of the signal moving. And so at this point, boom, right there, it crossed my threshold, and then it keeps going up and it's above the threshold, and then it starts falling back down, and then boom, right there, it crosses the threshold again. So that's two different crossings. And I know that as this thing moves, I would expect every time a single arm moves, in front of and away from my sensor, I'll get two crossings like that. So there'll be that initial crossing right here and the second crossing after it. So then given the amount of time, the amount of time that I've been sampling my values and the number of times that I've crossed going up and crossed going down on my signal, then I know how many peaks I saw. Because if I divide that number of crossings by 2, then I know there's just, there's going to be one of those values for each of the peaks effectively. So in this signal right here, let's say 800 is my my kind of threshold value that I'm snapping. If I count the number of crossings, I've got one crossing going up, I've got another crossing going down, so that's 2 crossings. And then I go back and I've got another crossing going up and another crossing going down. So that's 4 crossings total. Divide that by 2, 4 divided by 2 equals 2. That tells me I have 2 peaks in this signal. And you can see exactly that from the output here. So you can see both those peaks inside of here. And then if I know, let's say that this whole signal was measured in like 50 milliseconds, then I know the time, if I saw 2 peaks within a 50 millisecond window, well, it must have been 50 milliseconds divided by 2 amount of time in between those peaks. So like 25 milliseconds in between each of those peaks. And if I know it takes 25 milliseconds for one arm to move to the next arm, then I know how fast this thing is spinning, because it's going to take 25 milliseconds times 3 for an entire revolution of my 3-arm spinner to spin around. So I just do some multiplication. And once I know how long it takes for my spinner to spin around, that's kind of your period of your signal. I can just invert that. I take 1 divided by my period, and that gives me my frequency value. That's the standard conversion from period to frequency. And frequency is telling me how often, how many times per second this thing is spinning around. So that's all the magic to this. But it turns out I don't actually set a fixed threshold value like that 800 value I was mentioning here. I actually try to get a little more clever, because like I said, this 800 value, in this reading, 800 works perfectly, but maybe in your lighting conditions, you might get a value that falls a little bit below 800, like 700. And so it's annoying to have to tune that value. So what I actually do is I compute what is the midpoint of my signal, and I use that as my threshold for when I count those peak crossings. So I can look at this signal, I can see here's this low value, it's around 400. Here's this high value, let's call it 900 or so, it's somewhere around there. So if I look at what's the value in between 400 and 900, so where is exactly the middle of that signal? And so that would be a value that's, let's say it's about 400 plus. So I want to look at the amplitude of my signal. So the amplitude from 400 to 900, so take 900 minus 400, that's going to be 500. So I've got 500 units. That's the kind of the amplitude or the height of this whole signal. If I cut that in half, that's going to be 250. So then I know, half of my amplitude is 250, or actually technically that's the amplitude of the sine wave, but half of that range is 250. So if I take my minimum value of 400, if I add 250 to it, that gets me in the 650 kind of range right here. So this is kind of the midpoint of my signal. And so that way, instead of counting the crossings up here at 800 at some fixed value, let's count the crossings at 650. So, as a first step, I first figure out from my signal, what is that amplitude or that magnitude? What is the difference from the highest peak to the lowest low value? If it's above some threshold, like 400, then I know I'm getting a strong signal like you see right here because, something's spinning in front of it. And then once I know that magnitude or that amplitude value, I'll cut it in half, and then I'll add it to the minimum value down here that I found, and that's going to give me my midpoint of my signal. So in this case, with this little view of it, we're seeing 650 or so is kind of the midpoint of my signal, and then go through and count the crossings. So, go through point by point and see, as your signal, like boom, right here, it moves past 650, and then it goes back up, and then it goes down, and then boom, it moves right past 650. And so I'm counting all of those crossings. And then once I've counted the crossings, I can just do some math to figure out, given the time that I took to measure my signal, how many crossings I saw, what's the frequency that it's spinning at. So that's exactly how the spinner code works. And I'll grab the code, we'll open up the example again, and I'll just kind of walk through what it looks like. So if we open up the tachometer example here, basically, so let's look at the code for this, and you'll see it's going to be pretty similar to what I was just showing. There's a few little differences that I have in here though. The first thing is in the setup, I turn on the pixels just like you saw before. So I clear them and I turn on the first 3 pixels as white, because as you saw, that helps make the signal a little bit stronger. It gets more light reflecting off of the spinner. And then what I do is I just delay for a period of time that's configured. So it's a second, like we saw before. And just every second, it's going to do a sample. It's going to take a bunch of samples. And then, okay, so after it delays for that sample period, then I go through and I actually just collect a bunch of samples. And the number of samples is defined by the sample depth at the top here, which I set to 512, which is exactly what I was showing in that example before. So, I take some number of samples and I just save them into an array, just like you saw before. In this case, though, I added an extra delay. And so I'm doing that because I want to be able to tune how long that window of samples takes to occur. And like I mentioned before, this is where you kind of get into the trade-offs of you can do samples very quickly. So I can sample, just within microseconds of each other, but I don't have enough memory to store like a full second of samples. So there's a trade-off in that the more samples you store, the longer period of time you're looking at, and the longer period of time you look at, the slower frequency you can detect. Because, imagine if something only changes once every 10 seconds, well, I have to collect at least 10 seconds of data to measure that. And actually, you have to collect 20 seconds of data to measure that. So, I'm obviously not going to be able to detect something that's moving at a frequency of like once every 10 seconds. But luckily your spinners are probably moving faster than that. So it's a trade-off here in that I don't have enough data to store all of my samples. But that's what I can tweak here is I can change how many samples I store and how much time I wait in between each sample. And so the less time I take in between each sample, the smaller this delay basically. That just means the faster a speed I can detect. But the more samples I need to store a longer number of samples. And I mentioned in the comments here, if you're using the Circuit Playground Express board, it has a lot more memory. You could set this to a much higher value, like 1024, like 10 kilobytes worth of samples effectively, because it has 32 kilobytes of memory. So experiment with, you could set this to much higher values and see if it helps you read. You could crank up the number of samples, try setting your sample depth to 1024.0, and then set your sample period to a really low value. Set this to maybe 100 microseconds in between each sample. And so this should be able to detect a very fast spinner, but also a very slow spinner. Well, maybe not super slow, but this will give you a wider range of samples. But you couldn't do this on the classic board because the classic board only has 2 kilobytes of memory. So 10 kilobytes of samples are not going to fit in 2 kilobytes of memory. So that's why I knock it back down to 512 right here. But anyways, this loop is exactly like I just showed in that little sampling loop that I was showing before in the little signal processing example I was looking at. This is exactly the same as this loop right here in my main code right here. It's just I've added that extra delay. But the one actual difference though is that before I get into that main loop, I actually grab what is the current time, the number of microseconds at the start of the loop, and then at the end of the loop, I actually compute how many microseconds elapsed during that entire loop. So, as I took all those samples, I want to keep track of how long it took for those samples to be taken so that I know within that window of time, once I count the number of crossings once I detect the frequency of it, I can figure out the period of my signal. Okay, so that's what's happening here is I'm just, taking the elapsed number of microseconds and just converting that into the elapsed number of seconds as a floating point value right here. So there are 1 million microseconds in a second, so I'm just doing that conversion right here. And so this elapsed variable now holds how many seconds elapsed during this window of sampling. Then the next step is I go through all of my samples and I look for what is the maximum value and what is the minimum value. Actually, let's open up our serial plotter again so I can kind of see. So, when I look at, here's a window of samples, I'm going to go through all of these samples and see what is the lowest value that I saw and what is the highest value that I saw within there. And that's what this loop does. So it just loops through every sample, and I'm just computing what's the minimum sample, what's the maximum sample, and I just go through and just compare every value to the minimum and maximum values and update it as I go. So that once I'm done with this block of code, now I know what is the range or the magnitude or the amplitude of my signal, because I can just look at, if I take my maximum value minus my minimum value, that's telling me what is the amplitude of my signal or that kind of magnitude of my signal. And then I can do a quick test to see if that amplitude is not larger than my threshold that I set in the configuration. I can just stop. I'll just return back and just restart my main loop. It's going to go back to the top. It's going to wait a second, and it's going to take another set of measurements again. So that's how it knows that, in this steady state where there's only like a 100 or so difference between my samples, I don't want to do anything. Whereas when I'm in my spinning state like this, there's a much higher difference in samples. So I go from like 400, there's like a 500 or so difference in my samples there. So that's what's happening here in this little check. I'm looking at the magnitude of my signal. Then I compute the midpoint, like I mentioned before. So I'm figuring out, once I get to this line of code, I know for sure I've picked up a strong signal. That magnitude is quite large. And now let's figure out what is that midpoint value? What is the exact middle of this signal? And so like I mentioned, I'm just going to grab my minimum value and just add half of my amplitude to it. I guess amplitude is kind of a misnomer. I should have probably called this magnitude, because the amplitude, if I remember correctly, is actually, with a sine wave, it's just the value from your midpoint up to the peak values. It's kind of half of your actual kind of signal value that you're looking at here. But regardless, this is a magnitude value. And so I'm just computing my midpoint is my minimum plus half of that magnitude that I measured before. And then at this point, I'm ready to go through and look for how many times does that signal cross. Let's see if I can get back to the serial plotter. I've lost it here. Where'd it go? There we go. It's back here. Now I want to go through. Now I know my midpoint value, and I just want to count how many times does the signal cross the midpoint going up, and how many times does it cross going down. So that I know the number of occurrences that it crossed that threshold, that midpoint. And that's what this little loop does right here. So I'm just going through each of the readings, and I look at each reading as a pair. So I start with the first two readings, and I compare them to each other. And I look and see if the second reading, if the P1 reading is, first I grab, for each pair of readings, I grab a P0 and a P1 reading. So the P0 reading is the later reading, and the P1 reading is the more recent reading. If that more recent reading is actually exactly equal to my midpoint, then I'm just going to fudge it and just say that must be a crossing. I'm just going to assume that it went up and kept on crossing, because you have to think about, there are multiple cases that could occur here. If I'm looking at 2 points, I might get a case where my first point is below that midpoint and my second point is above it, in which case the midpoint happens somewhere in between there, and so that's pretty easy to detect. But there might be a case where my first point is below it and my second point is exactly on the midpoint, so I want to still detect that case. And that's kind of what this little case is doing right here. So I look and see if my second value is on the midpoint, I assume that that's a crossing, or if my midpoint, if my first midpoint is below, or if my first value is below the midpoint, if my second value is above the midpoint, then that's kind of this case right here where I'm catching a rising part of my signal. And then I'm also looking for the falling part of the signal, which is just the exact opposite. So if my first value is above the midpoint and if my second value is below the midpoint, then I'm just going to catch that as a falling signal here, so that, you know, now the signal is starting to fall and I caught that crossing below the midpoint here. And I'm careful, I don't actually look at my first sample value being equal to the midpoint, because I know the way this loop works, it's going to go through and, you know, this P1 value is going to be set for every single sample. So, you know, if any of the samples hits that midpoint, whether it's rising or falling, it's going to get counted by this little check right here. So it's not super obvious from this loop, but that's really what's happening. So once I hit one of these conditions, then I just increment the number of crossings. So I start with 0 crossings, and I just go through a pair of points at a time and look and see, where do I find those cases where those pairs of points either straddle the midpoint or the end actually hits the midpoint, and I count that as a crossing of my signal. And then after that, it's really easy. It's just math. So I know at this point how many times I crossed the midpoint, which is kind of telling me how many peaks I saw on my signal. And I know the period, the amount of time that I took to do that number of samples. So I can figure out the period of my signal. And the way I do that is I take my number of crossings and I divide it by 2, because, like I mentioned, for each time an arm of the spinner moves in front of the sensor, you know, I'm going to see the signal go up and then it's going to go back down. So I'm going to see 2 crossings of the midpoint there. So if I divide my crossings by 2, then that's kind of telling me, okay, how many arms of the spinner did I see? And then if I also divide by that number of arms in the spinner that I defined ahead of time, like at the top, I have a value of 3 right here, so this spinner has 3 arms on it, then that kind of normalizes this period value so that, you know, for one complete revolution of all 3 arms of this spinner, which is actually going to be 6 crossings, because, you know, imagine for this arm, it's going to cross going up, it's going to cross going down. And then as this arm moves, it's going to cross going up and then going down again. And then as this arm moves, it's crossing up and down. So that's 6 whole crossings that I saw. That is effectively 1 revolution of my spinner. So this period is kind of telling me the amount of time in seconds that it took for 1 full revolution of my spinner. And once I know that period value, I can actually just take the inverse of it. So this line right here, where I take 1 divided by my period, that gives me my frequency. So that's the number of times per second that 1 revolution takes for this spinner. And then if I want to convert that into the revolutions per minute value instead of revolutions per second, just multiply by 60, because there's 60 seconds in a minute. So take my frequency times 60, and that's what I get. And then I just print out the values in the example here. So that's exactly what's happening. So, you know, let's load up this tachometer sketch again, and we'll see the output here. But that's how this works. You know, basically it's just some signal processing effectively that I'm doing. It's not even really that advanced in the sense that I'm not, you know, like I mentioned, there's all this complex stuff you can get into, like the Fourier transforms, but I don't necessarily have to do that. You know, I know that this is a sine wave signal that always goes up and down, and, you know, I know the shape of this signal effectively, and so I can make some assumptions based on that shape, and that, you know, instead of like trying to do this really in-depth frequency analysis, I just look at my signal and know that it's always going to rise and it's always going to fall. And if I just count how often that happens, I can detect the frequency of this. Okay, so I loaded my sketch up. Let's open our serial monitor again, and I should hopefully be able to see the frequency or the speed of this device, of this spin. So there we go. Yeah, 16, 15 times a second, you know, 800, 900 RPMs or so of speed. It's nice that you can see it slows down a bit as the spinner itself slows down. I have to make sure to hold it in front of the light sensor, because, you know, if I move it away from the light sensor, that signal's not going to be as strong, so I have to hold it in front of the sensor. But we'll see, it should be able to slow down, and this thing should be able to detect down to like a 1 hertz signal or so. I calculated it out before, so let's just see how this thing goes. It's like 6 times a second, 5 times a second. Let's see, how's it going? Down to like 4 times a second. curious to see how well this can go. I actually haven't let it go this far before, so yeah, we're down to like almost twice a second. I want to see if I can get it down to once a second, if that's if it's able to detect that. Let's see how it goes. Yeah, that's looking like once a second. I mean, you can see this thing spinning. It's going to make 3 of the arms are going to spin in a second, but that looks pretty accurate to me. So I'm pretty confident in the results of this tachometer. So, okay, so I'm going to wrap this up. This is about an hour long, so I don't want to go too much longer. Like I mentioned, this is the circuit playground fidget spinner tachometer. So this is a way to detect the revolutions per second of a fidget spinner using the light sensor that's built into Circuit Playground. And there are 2 examples that I showed. So this one uses the little LED display, and it's showing the revolutions per second on that display, whereas this one is using just the serial monitor output that you saw right here. Both these examples are in the Circuit Playground library. Like I mentioned, if you're viewing this the day after I made this video, you probably won't see those in the library yet, so you'll need to go to the GitHub repository and pull these examples down to make this work and load this example up. So like I said, this was the Arduino version. I think it is possible to do this in CircuitPython because, I mean, the basic idea, all of the math for sure is possible. The only tricky thing is, can I sample my spinner fast enough to detect very high speeds? So like if I get rid of that example, let's go back to the code. So, you know, my main loop right here where I'm sampling my my spinner, kind of my light sensor values, as long as I can sample this fast enough to detect, you know, like 20 times a second, you know, as long as I can sample this, let's say 50 times a second, that means I could detect like a 25 times a second. I could detect a signal that changes that fast. As long as I can sample like 50 times a second, I should be able to do this in CircuitPython. So I think I'll try to do a version in CircuitPython to see if this will work. Because once I have that window of samples, then it really doesn't matter how fast or how slow it takes to do this math. You know, it's just doing the computations of figure out that midpoint, count the crossings and whatever. You know, that happens just once a second anyway, so who cares how slow that math is? It's really just this main little loop right here where it needs to sample very quickly. And so that's maybe going to be the difference in our Arduino sketch versus a Python sketch. So the Python sketch is going to run a lot slower in this loop, but as long as it runs at least 50 times a second, it should be fast enough to do this. So maybe tune in next week. I'll see if I can do a CircuitPython version of this fidget spinner, which will be a cool kind of example, a good way to compare Python versus Arduino code. Anyways, I'll wrap this up. If folks have questions, throw them into the chat, and I'll see if I can get to them. I don't see too many other questions in there right now, though. So let's see. I'll go to the main headshot here. So let's see. Oh, someone's asking, can the fidget spinner hit 88 miles per hour? I don't think I can do it with my hand, but I don't know, someone maybe could potentially get 88 miles per hour. You're going to see some serious stuff when that happens, so be careful. Anyways, I don't see any questions, so I'll wrap this up. Thanks a lot for watching. Check out youtube.com/Adafruit. You'll see this video and all kinds of other project videos on there. Check out learn.adafruit.com, and next week I'll have this written up as a project so that you'll be able to see. Check out blog.adafruit.com. That's the Adafruit blog. We'll publish out on the blog when this is published there. But that'll show you how to wire this up if you're doing like the 7-segment display and you're not sure how to connect that. And then check out twitch.tv/Adafruit. That's where I like to do these live streams. Every Friday I usually do a live stream. So tune into that. And like I said, I'm going to see if I can do a Python version of this fidget spinner tachometer. And it really just comes down to how fast can I sample things in the Python code. So I think it's going to be doable. Anyways, check that out. If you like this stuff, click the like, the comment, the subscribe button. Let us know that this is useful content, and we'll keep making projects and fun stuff like this. So until next time, this is Tony from Adafruit. So thanks for watching. I'll see you later. Bye.